Imagine something with me for a moment. Imagine you could take the entire Earth, every mountain, every ocean, every forest, every city, every grain of sand on every beach, all 7 continents, all the water in every river and lake, the molten iron core deep beneath your feet, every single atom that makes up this planet we call home, and you could squeeze it, compress it, crush it down smaller and smaller and smaller until it was no longer the size of a planet, no longer the size of a country, no longer the size of a city, not even the size of a house, not the size of a basketball, not the size of a golf ball, but smaller still, down to the size of a marble, and then even smaller than that, down to something you could barely see with the naked eye, a tiny speck, and then you kept going, smaller and smaller, past the point where any microscope could see it, past the point where the very concept of size begins to lose meaning. What would happen? What would that object become? What would the laws of physics say about something so incredibly, impossibly dense? The answer, and I need you to really sit with this for a moment, the answer is that you would create something called a singularity, a point where the rules of the universe, the laws that govern everything from the way an apple falls from a tree to the way galaxies spin through the cosmos, those rules simply stop working. They break. They produce nonsensical answers. They give us infinity. And in physics, infinity is not a triumph. Infinity is a cry for help. Infinity is the universe's way of telling us that we have reached the absolute edge of human understanding, and beyond that edge, we do not know what is real. Now, before we dive deep into this, and we are going to dive very deep today, I want you to know something. This is not going to be a surface-level discussion. This is not going to be a 5-minute explanation with some pretty animations and a catchy thumbnail, and then we move on. No. Today we are going to spend serious time together, you and I, exploring what might be the single most profound concept in all of physics. We are going to start from the very beginning, from the foundations of gravity itself, and we are going to build our understanding step by step, layer by layer, until we arrive at the very heart of reality, at the place where space-time itself comes to an end, at the singularity. And by the time we are done, you will understand this concept more deeply than the vast majority of people on this planet, including many people who have taken university-level physics courses. Because understanding a singularity is not just about memorizing a definition. It is about understanding gravity, understanding space-time, understanding quantum mechanics, understanding the life and death of stars, understanding the origin of the universe itself, and then understanding why all of these things converge at a single concept that we still cannot fully explain. So let me give you a taste of what is coming. Let me give you some facts that should, if I am doing my job right, make the hairs on the back of your neck stand up. Fact number 1. If you could compress our sun, this massive ball of fire that is 1.3 million times the volume of Earth, if you could compress it into a sphere just 6 kilometers across, about the size of a small town, it would become a black hole. And at its center, according to our best theory of gravity, there would be a singularity, a point of infinite density. Infinite, not very large, not unimaginably huge, infinite. That is what the mathematics says. Fact number 2. Right now, as you are watching this at the center of our Milky Way galaxy, there is an object called Sagittarius A star. It is 4 million times the mass of our sun. 4 million suns compressed into a region smaller than our solar system. And at its very center, according to general relativity, there is a singularity. You are living in a galaxy that has a singularity at its heart. Fact number 3, and this one is the one that really gets me. According to the Penrose-Hawking singularity theorems, which we will discuss in great detail later, the entire universe, everything you see, everything you have ever known, every star, every planet, every galaxy, every atom in your body, all of it emerged from a singularity. The Big Bang itself was a singularity. The origin of everything was a point where physics broke down completely. We exist because of a singularity. And fact number 4, even Albert Einstein, the man whose theory of general relativity predicted singularities in the first place, did not believe they were real. He published a paper in 1939 explicitly arguing that singularities could not form in nature. He thought there had to be some mechanism that prevents them. He was, as it turns out, almost certainly wrong about that. Singularities, or at least the conditions that lead to them, appear to be an inevitable feature of our universe. So today, we are going on a journey. We are going to explore what a singularity really is, not the pop science version, not the Hollywood version, but the real, deep, mathematical, physical, philosophical truth about singularities. We are going to cover gravity from Newton to Einstein. We are going to cover the birth and death of stars. We are going to go inside a black hole and describe what happens step by step as you fall toward the singularity. We are going to explore the Big Bang and ask whether the universe really began from a singularity. We are going to confront the clash between general relativity and quantum mechanics and understand why that clash happens precisely at singularities. We are going to explore string theory, loop quantum gravity, and other cutting-edge attempts to resolve singularities. We are going to discuss the information paradox, the firewall paradox, cosmic censorship, naked singularities, white holes, wormholes, baby universes, and the fundamental question of whether infinity actually exists in nature. And through all of it, we are going to maintain our curiosity, our wonder, and our honesty about what we know and what we do not know. Because the story of singularities is ultimately the story of human knowledge pushing up against its own limits, and that is one of the most beautiful stories in all of science. Let us begin where all of gravity begins. Let us begin with Isaac Newton. The year is 1687. Isaac Newton, a man who by this point has already invented calculus and done groundbreaking work on optics, publishes a book called the Principia Mathematica. This book will change the course of human history. In it, Newton describes something he calls the universal law of gravitation. The idea is deceptively simple. Every object that has mass attracts every other object that has mass. The strength of that attraction depends on two things and two things only. First, the masses of the two objects. More massive objects pull harder. Second, the distance between them. The closer they are, the stronger the pull. Newton captured this in a beautifully simple equation. The force of gravity between two objects equals the gravitational constant, a number we call g, multiplied by the mass of the first object, multiplied by the mass of the second object, all divided by the square of the distance between their centers. F equals g times m 1 times m2 divided by r squared. This single equation explained why apples fall from trees, why the moon orbits Earth, why planets orbit the sun, why tides rise and fall. It was staggeringly successful. For over 200 years, Newton's law of gravity was the law. It predicted the motions of planets with extraordinary precision. It allowed astronomers to discover Neptune before anyone had ever seen it, simply by noticing perturbations in the orbit of Uranus and calculating where a hidden planet must be. Newton's gravity was one of the greatest triumphs of the human mind. But here's the thing that most people do not notice about Newton's equation, and this is crucial for our story. Look at that equation again. F equals G m1 m2 over r squared. Now, what happens when r, the distance between the two objects, becomes very, very small? As r decreases, the force increases. That makes intuitive sense, but what happens when r approaches zero? When the distance between the centers of the two objects becomes zero? Well, you are dividing by r squared, and r is approaching zero. So you are dividing by a number that is approaching zero. And when you divide by something approaching zero, the result approaches infinity. Newton's equation, the simplest and most successful equation of gravity, already contains within it the seed of the singularity problem. When two masses occupy the same point, the force between them becomes infinite. Newton himself was not overly troubled by this because, in practice, two objects cannot occupy the same point. They have physical size. They push against each other. But the mathematical hint is there right from the start, from the very first equation of gravity. Infinity lurks in the mathematics, waiting. Newton's gravity had another problem, one that Newton himself was aware of and deeply uncomfortable with. How does gravity reach across empty space if the sun pulls on the Earth, and the Earth is 150 million kilometers away? How does the pull get there? What is the mechanism? Newton's equations described the effect perfectly, but said nothing about the mechanism. Gravity seemed to act instantaneously across any distance, which Newton found deeply unsatisfying. He wrote, and I am paraphrasing here, that the idea of one body acting on another through a vacuum at a distance, without anything in between to carry the influence, was so absurd that he believed no person with any competence in philosophical thinking would ever fall for it. And yet, his equations worked beautifully regardless. The mechanism remained a mystery for over 200 years until a patent clerk in Bern, Switzerland, figured it out. But before we get to Einstein, let us pause and appreciate the cracks that were appearing in Newton's universe by the late 1800s and early 1900s. The biggest one was Mercury. Mercury, the closest planet to the Sun, has an orbit that is slightly elliptical, as all planetary orbits are. And the point of closest approach to the Sun, called the perihelion, shifts slightly with each orbit. This shifting, called the precession of the perihelion, happens partly because of the gravitational pull of other planets. Astronomers could calculate exactly how much precession should occur due to known gravitational influences. But when they compared their calculations to the actual observed precession of Mercury, there was a discrepancy, a tiny one. 43 arc-seconds per century. That is an incredibly small amount. It would take thousands of years to even notice it with the naked eye. But astronomers were precise people, and they knew something was off. Some proposed a hidden planet even closer to the Sun, which they called Vulcan. Others wondered if Newton's law needed modification. The answer, when it came, was more revolutionary than anyone expected. In 1905, Albert Einstein had what is sometimes called his miracle year, his annus mirabilis. He published 4 papers that would each, individually, have been enough to make him one of the most important physicists of his generation. One introduced the special theory of relativity. One explained the photoelectric effect and helped lay the foundations for quantum mechanics, which actually won him the Nobel Prize. One explained Brownian motion and helped prove the existence of atoms. And one gave us the most famous equation in all of science, E equals mc squared, which showed that mass and energy are two forms of the same thing, interchangeable, with the conversion factor being the speed of light squared. The speed of light squared is an enormous number, which is why a tiny amount of mass contains an enormous amount of energy, as nuclear weapons so devastatingly demonstrated. But for our story, special relativity is the key. Einstein showed that the speed of light in a vacuum is always the same, no matter how fast you are moving. This sounds innocent enough, but its consequences are earth-shattering. It means that space and time are not separate, absolute things. They are woven together into a four-dimensional fabric called spacetime. It means that time passes differently for observers moving at different speeds. It means that lengths contract, that masses increase, that simultaneity is relative. It means that nothing, absolutely nothing, can travel faster than light. And this creates a problem for Newton's gravity, because Newton's gravity acts instantaneously. If the sun suddenly vanished, Newton's equations say Earth would immediately fly off in a straight line, instantly. But special relativity says nothing can travel faster than light, including gravitational influence. So information about the sun's disappearance should take about 8 minutes to reach Earth, the same time light takes. Newton and Einstein could not both be right. Something had to give. Einstein spent the next 10 years, from 1905 to 1915, working on this problem. It nearly broke him. He struggled with incredibly complex mathematics. He made errors. He went down blind alleys. He despaired. But in November 1915, he presented to the Prussian Academy of Sciences his general theory of relativity, and the world of physics was never the same. The core idea of general relativity is breathtaking in its simplicity and profound in its implications. Gravity, Einstein said, is not a force at all. Newton was wrong about the fundamental nature of gravity. Gravity is not one object pulling on another across empty space. Instead, gravity is geometry. Gravity is the curvature of space-time itself. Here's what that means. Imagine a large rubber sheet stretched flat. This represents space-time in the absence of mass. Now place a heavy bowling ball on the sheet. The sheet deforms, curves, creates a dip around the bowling ball. Now roll a marble across the sheet. The marble does not travel in a straight line. It curves toward the bowling ball, not because the bowling ball is pulling it, but because the sheet itself is curved. The marble is following the most natural path through curved space. This is essentially what gravity is in Einstein's picture. The sun does not reach out and pull on the Earth. The sun's enormous mass curves the space-time around it, and the Earth follows the most natural path through that curved space-time, which happens to be an orbit. Objects in free fall are not being pushed or pulled. They are following the straightest possible paths, called geodesics, through curved space-time. Gravity is not a force. It is the shape of the universe. Einstein encoded this idea in a set of equations now known as Einstein's field equations. Written compactly, they look like this. G mu nu plus lambda. G mu nu equals 8 pi g over c to the fourth, multiplied by T mu nu. The left side of the equation describes the geometry of space-time, how it curves and bends. The right side describes the distribution of matter and energy, what stuff is present and how it is arranged. The equation says, in essence, that matter and energy tell spacetime how to curve, and the curvature of spacetime tells matter and energy how to move. This relationship is dynamic, feedback-driven, and incredibly complex. Solving Einstein's field equations exactly is extraordinarily difficult. In most cases, it is impossible, and physicists must resort to approximations. But in certain simplified symmetric cases, exact solutions can be found, and those exact solutions would reveal something terrifying. But first, let us appreciate what general relativity immediately accomplished. Remember Mercury's orbit? That persistent 43 arcsecond discrepancy that had haunted astronomers for decades? Einstein calculated the orbit of Mercury using general relativity instead of Newton's gravity, and the discrepancy vanished. General relativity predicted exactly the right amount of precession, exactly, to the arcsecond. Einstein later said that when he saw this result, he was so excited that he had heart palpitations. He knew his theory was correct, and there was more. General relativity made predictions that Newton's theory could not. It predicted that light itself would be bent by gravity, because photons, like everything else, follow the curvature of spacetime. In 1919, during a total solar eclipse, the British astronomer Arthur Eddington measured the positions of stars near the Sun and found that their apparent positions were shifted exactly as Einstein predicted. Light was being deflected by the Sun's gravity. The news made front-page headlines around the world. Einstein became the most famous scientist in history, a status he retains to this day. General relativity also predicted gravitational time dilation, the fact that time passes more slowly in stronger gravitational fields. This is not a theoretical curiosity. It is a practical reality. The GPS satellites orbiting Earth run their clocks at a slightly different rate than clocks on the surface, and if we did not correct for gravitational time dilation using Einstein's equations, GPS would accumulate errors of about 10 kilometers per day. Every time you use your phone's navigation, you are relying on general relativity. Einstein also predicted gravitational redshift, the stretching of light waves as they climb out of a gravitational field, which has been confirmed experimentally many times. And he predicted gravitational waves, ripples, in space-time itself, caused by accelerating masses, which were finally detected directly in 2015 by the LIGO experiment, 100 years after Einstein predicted them. Every single prediction of general relativity has been confirmed. It is one of the most thoroughly tested and successful theories in the entire history of science. And yet, this theory, this spectacularly successful theory, contains within it a prediction so extreme, so bizarre, so disturbing, that even Einstein himself refused to believe it. That prediction is the singularity. Now, I want you to really engage with this because we are about to enter the heart of our story. If you are enjoying this deep dive so far, if you appreciate the fact that we are taking the time to really build this understanding properly from the foundations up, then I want you to do something for me. Hit that like button right now. It takes 1 second and it makes a huge difference. And while you are at it, drop a comment telling me where you are watching from. What city? What country? I am genuinely curious about how far this video reaches. Are you in Karachi, Mumbai, London, New York, Dubai, Tokyo, Lagos, Sao Paulo? Wherever you are, let me know, because this is a global conversation we are having, and I want to know who is part of it, all right? Let us now talk about the man who first found the singularity hiding in Einstein's equations and the extraordinary circumstances under which he found it. The year is late 1915 and early 1916. World War I is raging across Europe. Millions of soldiers are dying in trenches, in mud, in poison gas attacks. The Eastern Front is particularly brutal, and on that Eastern Front, serving as a German soldier, is a man named Karl Schwarzschild. Schwarzschild was not an ordinary soldier. He was a brilliant physicist and astronomer who had been the director of the Astrophysical Observatory in Potsdam. Despite being in the middle of a war, despite being surrounded by death and suffering, Schwarzschild obtained a copy of Einstein's newly published general relativity equations, and he began working on them in the trenches during a war, and he solved them. Schwarzschild found the first exact solution to Einstein's field equations. His solution described the space-time geometry around a perfectly spherical, non-rotating, uncharged mass. It is called the Schwarzschild solution, or the Schwarzschild metric. He mailed his solution to Einstein, who presented it to the Prussian Academy of Sciences in January 1916. Einstein was astonished. He had not expected anyone to find an exact solution so quickly, and certainly not a soldier writing from the front lines. Tragically, Karl Schwarzschild never lived to see the full implications of his work. He contracted a painful autoimmune disease, pemphigus, while serving on the front, and he died in May 1916 at the age of just 42. But his solution would go on to reveal one of the most profound secrets of the universe. The Schwarzschild solution contains a number that is now named after him, the Schwarzschild radius. For any given mass, there is a critical radius, and that radius is given by the formula R equals 2gm over c squared, where g is the gravitational constant, m is the mass of the object, and c is the speed of light. For the Earth, the Schwarzschild radius is about 9 millimeters. For the Sun, it is about 3 kilometers. For a star 10 times the mass of the Sun, it is about 30 kilometers. Now, under normal circumstances, this radius is deep inside the object, and it has no physical significance. The Sun's Schwarzschild radius is 3 kilometers, but the Sun itself has a radius of about 700,000 kilometers. So the Schwarzschild radius is buried far beneath the surface, where the solution does not apply in the same way. But here is the question that the Schwarzschild solution forced physicists to confront. What if an object were compressed so much that its physical radius became smaller than its Schwarzschild radius? What if all the mass of the Sun were squeezed into a sphere less than 3 kilometers across? The answer is that something extraordinary happens. At the Schwarzschild radius, a boundary forms. This boundary is called the event horizon. And the event horizon is one of the most remarkable concepts in all of physics. It is not a physical surface. You cannot touch it. There is no wall there, no barrier, no membrane. It is a boundary in space-time itself, a point of no return. At the event horizon, the escape velocity, the speed you would need to travel to escape the gravitational pull, equals the speed of light. And since nothing can travel faster than light, nothing that crosses the event horizon can ever escape. Not light, not radiation, not information, not anything. Once you cross the event horizon, you are cut off from the rest of the universe, absolutely and irrevocably. There is no coming back. There is no signal you can send. You are gone. This is a black hole. The term would not actually be coined until decades later in 1967, when the physicist John Archibald Wheeler used it in a lecture. But the concept was there in Schwarzschild's 1916 solution. An object so dense that its gravitational influence creates a region from which nothing can escape. But the event horizon, as strange as it is not the truly terrifying part of the Schwarzschild solution. The truly terrifying part is what lies at the center, at the very center of the Schwarzschild solution, at the point where r equals 0. The mathematics does something catastrophic. The curvature of spacetime, which is a well-defined finite quantity everywhere else, becomes infinite at r equals 0. The density of the collapsed mass, assuming all the mass ends up at the center, becomes infinite. The equations themselves break. They produce divisions by 0. They produce infinities. They produce mathematical nonsense. This is the singularity. Not a very dense object, not a very small object, a point where the mathematical description of reality itself ceases to function, where the equations that describe space-time, that describe gravity, that describe the fabric of reality, return answers that are undefined, infinite, meaningless. Let me be very clear about what this means, because it is often misunderstood. When physicists say that physics breaks down at a singularity, they do not mean that strange things happen. They do not mean that the physics is merely unusual or exotic. They mean that the equations literally cannot produce meaningful answers. It is as if you ask someone to divide 10 by 0 on a calculator. The calculator does not give you a very large number. It gives you an error. It says, this operation is undefined. That is what happens at a singularity. General relativity, our best theory of gravity, our most successful description of spacetime, encounters a point where it returns an error message. Undefined. Cannot compute. Does not know. Now, when Schwarzschild's solution was first analyzed, there was enormous confusion about the significance of these problematic points. There appeared to be two trouble spots, one at the Schwarzschild radius, where some terms in the equations also seemed to blow up, and one at r equals 0. Physicists spent decades trying to understand whether these were physically real problems or merely artifacts of the particular mathematical coordinates they were using. Think of it this way. If you look at a map of the Earth, the North Pole can look very strange depending on the map projection you use. On a Mercator projection, the North Pole is stretched out into an infinitely long line at the top of the map. But there is nothing actually wrong with the North Pole. The strangeness is an artifact of how we drew the map, not a property of the Earth itself. This is called a coordinate singularity, a point that looks problematic in one set of coordinates, but is perfectly fine in another. In 1960, the mathematicians Martin Kruskal and George Sekaris independently found a new set of coordinates for the Schwarzschild solution that revealed the truth. In Kruskal-Sekaris coordinates, the event horizon is perfectly well behaved. There is nothing singular about it. The apparent singularity at the Schwarzschild radius was a coordinate singularity, an artifact of the original coordinates. The event horizon is a remarkable boundary with extraordinary properties, but it is not a place where physics breaks down. Space-time at the event horizon is smooth, well-defined, and well-behaved. But r equals 0? That is a different story entirely. No change of coordinates can remove the singularity at r equals 0. In any coordinate system, in any mathematical framework, the curvature of spacetime at r equals 0 is infinite. This is what physicists call a genuine curvature singularity, as opposed to a mere coordinate singularity. It is a real feature of the Schwarzschild geometry, not an artifact of how we describe it. And this is what makes it so profoundly disturbing. It is not a problem with our description. It appears to be a problem with reality itself, or at least with our best theory of what reality is. Einstein, confronted with this implication of his own theory, refused to accept it. In 1939, he published a paper in the Annals of Mathematics titled On a Stationary System with Spherical Symmetry, consisting of many gravitating masses, in which he attempted to demonstrate that singularities could not form in nature. His argument was essentially that the physical processes involved in gravitational collapse would prevent matter from ever being compressed within its Schwarzschild radius. Other prominent physicists, including Arthur Eddington, the very man who had confirmed Einstein's prediction of light bending, also rejected the idea. Eddington once famously dismissed the work of the young Indian physicist Subrahmanyan Chandrasekhar, who had shown that stars above a certain mass could not be supported against gravitational collapse, calling it stellar buffoonery. The scientific establishment of the early 20th century was deeply resistant to the idea that nature could produce singularities. They felt intuitively that it was absurd for physical quantities to become infinite. Surely, something must intervene. The question of whether singularities could actually form in the real universe brings us to one of the most dramatic stories in all of astrophysics, the death of stars. Because singularities do not just appear out of nowhere. In our universe, the primary way that singularities form, or at least the primary way we know about, is through the gravitational collapse of massive stars at the end of their lives. And to understand this, we need to understand how stars live, how they die, and why some of them die in a way that produces the most extreme objects in the cosmos. A star is, at its most fundamental level, a battleground. Two forces are locked in a constant titanic struggle. On one side is gravity, the force that pulls every atom of the star toward the center, trying to crush the entire object down into the smallest possible volume. On the other side is radiation pressure, the outward push generated by the nuclear fusion reactions happening in the star's core. In the core of our sun, hydrogen atoms are being fused together to form helium. This process releases enormous amounts of energy, which creates an outward pressure that pushes against gravity. And as long as these two forces are in balance, a state called hydrostatic equilibrium, the star is stable. It shines. It persists. Our sun has been in this state of balance for about 4.5 billion years. And it will continue for roughly another 5 billion years. Stars like our sun live a very, very long time, but fusion fuel is finite. Eventually, the hydrogen in the core runs out. When this happens, the battle between gravity and radiation pressure shifts. Without fusion energy to generate outward pressure, gravity begins to win. The core contracts, heats up, and if the star is massive enough, it begins fusing the helium into heavier elements like carbon and oxygen. This buys the star more time, but not forever. Each successive round of fusion produces heavier elements, from carbon to neon to oxygen to silicon, and each round lasts for a shorter and shorter time, because each produces less energy and gravity keeps gaining ground. A massive star can fuse elements all the way up to iron in its core. But iron is the end of the line. Fusing iron does not release energy. It requires energy. So when the core becomes iron, fusion stops. The outward pressure vanishes, and gravity, which has been waiting patiently for billions of years, finally wins. What happens next depends entirely on the mass of the star, and this is where the story splits into three possible endings, three possible fates. And only one of them leads to a singularity. The first fate is for stars roughly like our Sun, stars with masses up to about 8 times the mass of the Sun. When these stars run out of fuel, their cores contract, but they are not massive enough to ignite fusion of the very heaviest elements. The outer layers of the star are gently expelled into space, creating a beautiful glowing shell called a planetary nebula, which has nothing to do with planets, but was named by early astronomers who thought they looked like planets through their telescopes. What is left behind is the core, now exposed, incredibly hot but slowly cooling, roughly the size of the Earth, but with a mass comparable to the Sun. This object is called a white dwarf. A white dwarf is extraordinarily dense. A teaspoon of white dwarf material would weigh about 15 tons. But it is not infinitely dense. Something is holding it up against further gravitational collapse. That something is called electron degeneracy pressure, and it comes from quantum mechanics. Here is how it works. One of the fundamental principles of quantum mechanics is called the Pauli exclusion principle, named after the physicist Wolfgang Pauli. It says that no two fermions, a category of particles that includes electrons, can occupy the same quantum state at the same time and place. In a white dwarf, the electrons are packed so tightly that they are being forced into the same quantum states. The Pauli exclusion principle says no. It generates an outward pressure, a quantum mechanical pushback, that resists further compression. This is not a thermal pressure from heat. It is a quantum mechanical pressure that exists even at absolute zero temperature. And it is this pressure that holds up the white dwarf against the relentless inward pull of gravity. But here's the thing. Electron degeneracy pressure has a limit. In 1930, a brilliant young Indian astrophysicist named Subrahmanyan Chandrasekhar, just 20 years old at the time, traveling by steamship from India to England to begin his studies at Cambridge, worked out that electron degeneracy pressure can only support a white dwarf up to a certain mass. That mass is about 1.4 times the mass of the Sun. This is now known as the Chandrasekhar limit, and it earned Chandrasekhar the Nobel Prize in Physics in 1983, more than 50 years after he calculated it. If a white dwarf exceeds this limit, electron degeneracy pressure fails. Gravity overwhelms the quantum mechanical resistance, and the collapse continues. The story of how Chandrasekhar was treated when he first presented this result is one of the great tragedies of scientific history. Arthur Eddington, one of the most respected astrophysicists in the world, publicly mocked and ridiculed Chandrasekhar's result. At a meeting of the Royal Astronomical Society, Eddington dismissed the work, essentially saying that nature could not possibly allow such an absurd outcome. Chandrasekhar was devastated. It took decades for the scientific community to fully accept his calculation. But he was right. Nature does allow it. Nature does not care about our comfort or our intuitions. The second fate is for stars with initial masses roughly between 8 and 25 times the mass of the Sun. When these stars exhaust their nuclear fuel, the collapse of the core is catastrophic and spectacular. The core collapses so rapidly that it triggers one of the most violent events in the universe, a supernova. In a fraction of a second, the core collapses from roughly the size of the Earth to a sphere about 20 kilometers across. The outer layers of the star are blasted outward at speeds up to 10% of the speed of light, releasing more energy in a few seconds than our Sun will release in its entire 10 billion year lifetime. A single supernova can briefly outshine an entire galaxy of hundreds of billions of stars. It is an event of almost incomprehensible violence. What is left behind after the supernova is the collapsed core, and it is no longer a white dwarf. It has been compressed so much that the electrons have been forced into the protons, a process called inverse beta decay, creating neutrons. The entire core is now essentially a ball of neutrons. This object is called a neutron star, and its density is beyond anything we can truly grasp. A teaspoon of neutron star material would weigh approximately 6 billion tons. 6 billion tons in a teaspoon? The entire mass of the Sun, or perhaps 1.5 to 2 solar masses, is packed into a sphere about 20 kilometers in diameter. That is roughly the size of a city. Imagine the mass of the Sun compressed into something that would fit inside the city limits of a mid-sized town. Some neutron stars spin at incredible rates, hundreds of times per second, and emit beams of radiation from their magnetic poles. When these beams sweep across our line of sight, we detect them as regular pulses. These are called pulsars, and they are so regular that when the first pulsar was discovered in 1967 by Jocelyn Bell Burnell, the signal was initially labeled LGM1, which stood for Little Green Men, because the researchers seriously wondered for a moment if they had detected an alien signal. A neutron star is held up by a mechanism analogous to what supports white dwarfs, but operating with neutrons instead of electrons. This is called neutron degeneracy pressure, and it is also based on the Pauli exclusion principle. Neutrons, like electrons, are fermions, and they resist being squeezed into the same quantum state. This quantum mechanical pressure holds up the neutron star against the immense gravitational force trying to compress it further. But just as electron degeneracy pressure has a limit, the Chandrasekhar limit, neutron degeneracy pressure also has a limit. This is called the Tolman-Oppenheimer-Volkoff limit, or the TOV limit, named after the physicists who calculated it, Richard Tolman, J. Robert Oppenheimer, the same Oppenheimer who later led the Manhattan Project, and George Volkoff. The TOV limit is approximately 2 to 3 solar masses, though the exact value is still uncertain because it depends on the detailed properties of matter at nuclear densities, which are not yet fully understood. But we know it exists. There is a maximum mass that neutron degeneracy pressure can support. And this brings us to the third fate, the one that leads to singularities. The third fate is for the most massive stars, those with initial masses above roughly 25 times the mass of the Sun, or more precisely, for any stellar core that exceeds the TOV limit after a supernova. When such a core collapses, neutron degeneracy pressure tries to hold it up and fails. And here is the crucial point, the point that makes this fate different from the other two. When neutron degeneracy pressure fails, there is no known force in the entire universe that can stop the collapse. Think about that for a moment. We have gone through the complete catalog of forces. Normal material forces like the electromagnetic forces between atoms that give solid objects their rigidity gave way long ago. Electron degeneracy pressure, a quantum mechanical effect, gave way at the Chandrasekhar limit. Neutron degeneracy pressure, another quantum mechanical effect, gives way at the TOV limit. There is nothing else. No known physics provides another mechanism that can halt the collapse. Gravity, patient and relentless, has overcome everything the universe has to throw at it, and so the collapse continues. The mass falls inward, passing through its own Schwarzschild radius. An event horizon forms. The object becomes a black hole. And according to general relativity, the collapse does not stop there. There is nothing to stop it. The mass continues to collapse, fallen inward, compressed to smaller and smaller volumes, denser and denser concentrations, until it reaches a single point. A point of zero volume, a point of infinite density, a point of infinite curvature, a singularity. This is what general relativity predicts, unambiguously. Unavoidably, every single black hole in the universe, according to our best theory of gravity, has a singularity at its center. This is not speculation. This is not hand-waving. This is what the equations say. And it is not just stellar black holes. There are also supermassive black holes, objects that sit at the centers of most, perhaps all, large galaxies. These are not just a few times the mass of the Sun. They are millions to billions of times the mass of the Sun. Sagittarius A star, the supermassive black hole at the center of our Milky Way, has a mass of about 4 million solar masses. Its event horizon has a radius of about 12 million kilometers, which is about a fifth of the distance between Mercury and the Sun. The supermassive black hole in the galaxy M87, which became the first black hole ever directly imaged by the Event Horizon Telescope in April 2019, has a mass of about 6.5 billion solar masses. 6.5 billion. Its event horizon is larger than our entire solar system. And at the center of each of these objects, according to general relativity, there is a singularity, an almost incomprehensible thought. The largest objects we know of, containing billions of solar masses, harbor at their very centers a point where the laws of physics break down entirely. How supermassive black holes form is, by the way, still one of the great unsolved mysteries of astrophysics. We observe supermassive black holes in the very early universe, when the universe was less than 1 billion years old. How did they grow so massive so quickly? Stellar black holes grow by accreting matter, but the rate at which they can accrete is limited by radiation pressure from the superheated, infalling material. It is very difficult to see how stellar black holes could have grown to billions of solar masses in the time available. Various mechanisms have been proposed, including direct collapse of enormous gas clouds without going through a normal star phase, rapid mergers of smaller black holes, and the existence of primordial black holes that formed in the very early universe. But the question is far from settled. It is an active and vibrant area of research. Now, I said earlier that Einstein did not believe singularities could form in nature. He was not alone. For decades, many physicists clung to the hope that singularities were merely an artifact of the perfect symmetry assumed in the Schwarzschild solution. After all, Schwarzschild assumed a perfectly spherical mass. Real stars are not perfect spheres. They rotate, they have lumps and bumps, they are messy, Maybe in a realistic, non-symmetric collapse, the infalling matter would miss the center, swirl around, bounce off itself, and avoid forming a singularity. Maybe the singularity was just a consequence of the mathematical idealization, not a feature of the real universe. This hope persisted for decades. It was a reasonable hope. After all, many mathematical models produce extreme results only when idealized assumptions are made, and those results go away when the model is made more realistic. But then Roger Penrose came along, and everything changed. In 1965, Roger Penrose, a British mathematician and physicist who was working at Birkbeck College in London, published a paper that would eventually earn him the Nobel Prize in physics. The paper was titled Gravitational Collapse in Spacetime Singularities, and it was only 3 pages long. 3 pages that changed our understanding of the universe. Penrose's approach was completely different from anything that had been tried before. Instead of trying to solve Einstein's equations for a specific collapsing configuration and checking whether a singularity appeared, Penrose used a branch of mathematics called topology to prove a much more general and powerful result. He introduced the concept of a trapped surface, a closed two-dimensional surface in space-time from which all light rays, even those pointing outward, are actually converging inward. In other words, a trapped surface is a region where gravity is so strong that even outward-directed light is being pulled inward. If a trapped surface forms, Penrose showed, then under very general conditions, essentially, that gravity is always attractive, and that matter satisfies certain reasonable energy conditions, a singularity must inevitably form, not might form, must. And crucially, this result did not depend on any symmetry assumptions. It did not matter whether the collapsing object was a perfect sphere or an irregularly shaped mess. It did not matter whether it was rotating or stationary. As long as a trapped surface forms, a singularity is unavoidable. This was the first singularity theorem, and it demolished the hope that singularities could be avoided by appealing to realistic, non-symmetric conditions. Let me emphasize what Penrose proved. He did not prove that singularities exist in some specific model. He proved that they are a generic, unavoidable feature of gravitational collapse in general relativity. Given reasonable physical assumptions about how matter and energy behave, once gravity becomes strong enough to form a trapped surface, the subsequent formation of a singularity is mathematically guaranteed. There is no escape. There is no loophole. Within the framework of general relativity, singularities are inevitable. This was revolutionary. But it was only the beginning. Because Stephen Hawking, who at the time was a young graduate student at Cambridge, saw Penrose's theorem and had an extraordinary insight. If Penrose could prove that singularities form when things collapse under gravity, going forward in time, then what if you reversed the argument? What if you applied the same logic going backward in time? If the universe is expanding now, which all observations confirm, then running the expansion backward means the universe was smaller, denser, and hotter in the past. Keep running it backward, and you reach higher and higher densities, stronger and stronger curvature, until you reach a state that satisfies the conditions of Penrose's theorem, but in reverse. Hawking realized that the same mathematical machinery that proved singularities form and gravitational collapse could be used to prove that the universe began from a singularity. The Big Bang was not just a period of high density, it was a singularity. a point where space-time itself began. Between 1966 and 1970, Hawking and Penrose collaborated on a series of increasingly powerful singularity theorems, culminating in the famous Hawking-Penrose singularity theorem of 1970. This theorem proved under very general conditions that singularities are a feature of general relativity in both directions. In the future, gravitational collapse producing black hole singularities, and in the past, the universe beginning from a Big Bang singularity. The implications were staggering. The entire observable universe, every galaxy, every star, every planet, every atom, every particle of light, all of it emerged from a singularity, from a point where the density, temperature, and curvature of space-time were infinite, from a state that our best theory of gravity cannot describe. Roger Penrose was awarded the Nobel Prize in Physics in 2020, more than 55 years after his original theorem, sharing it with Andrea Ghez and Reinhard Genzel for their observational work confirming the existence of the supermassive black hole at the center of our galaxy. It was a deeply fitting recognition because Penrose's work provided the theoretical foundation proving that the singularities at the centers of black holes are not optional, not avoidable, not artifacts. They are consequences of gravity itself. But here is the profound subtlety that is often missed in popular accounts of the singularity theorems. What the theorems actually prove is that singularities are inevitable within the framework of general relativity. But what if general relativity itself is not the whole story? What if general relativity is an incredibly good approximation that works spectacularly well in most situations, but breaks down in the extreme conditions near a singularity? After all, we know that general relativity is not a complete description of nature. It does not include quantum mechanical effects. And at the extreme densities and tiny scales associated with singularities, quantum effects must become important. The singularity theorems prove that GR predicts singularities. They do not prove that singularities actually exist in nature. They might instead be proving that general relativity has limitations, that it breaks down at extreme conditions and needs to be replaced by a more fundamental theory. And this, many physicists believe, is the deeper message of the singularity theorems. Singularities are not features of reality. They are features of our current theory. They are symptoms of our theory's incompleteness. They are the universe's way of telling us that we need better physics. Now, Penrose had another profound insight related to singularities, one that he proposed in 1969 and that remains unresolved to this day. It is called the cosmic censorship conjecture, or sometimes the cosmic censorship hypothesis. Penrose noticed that in all known solutions to Einstein's equations where singularities form, the singularity is hidden behind an event horizon. You cannot see it from the outside. It is clothed, dressed, censored, hidden from view. Penrose proposed that this is not a coincidence but a general principle of nature. He conjectured that every singularity that forms from gravitational collapse is always hidden behind an event horizon. No naked singularity, no singularity visible to the outside universe ever forms. The weak cosmic censorship conjecture states that no singularity formed from realistic gravitational collapse is visible to distant observers. Every singularity is hidden behind an event horizon. The strong cosmic censorship conjecture is a stronger statement that deals with what happens inside the black hole, essentially asserting that the interior geometry, while containing a singularity, does not allow the singularity's unpredictability to affect the region of spacetime accessible to observers. Why does this matter? Because if cosmic censorship fails, if a naked singularity can exist, visible to the rest of the universe without an event horizon to hide it, then the unpredictability of the singularity, the fact that physics breaks down there, would not be contained. It would leak out into the observable universe. We could not predict what happens near a naked singularity because the laws of physics break down there. Determinism, the principle that the present determines the future, would fail. The universe would become fundamentally unpredictable, not just in the quantum mechanical sense we are already familiar with, but in a much deeper, more troubling sense. The very framework of physics would collapse. Is cosmic censorship true? We do not know. More than 50 years after Penrose proposed it, the conjecture remains unproven. There are theoretical scenarios carefully constructed and somewhat contrived in which naked singularities appear to form. But most physicists believe these scenarios are not physically realistic. The general expectation, the scientific bet, if you will, is that cosmic censorship is true, at least in the weak form. Nature hides its singularities. But proving it mathematically has been one of the most stubborn problems in mathematical physics. Some researchers have spent their entire careers on it without resolution. It remains one of the great open questions in our understanding of gravity. Let us now do something truly extraordinary. Let us go inside a black hole. Let us take a journey, a thought experiment, from the outside of a black hole, past the event horizon, and down toward the singularity. And let us see what happens, step by step, according to our best understanding of physics. We will consider two perspectives, because one of the most mind-bending aspects of black holes is that what you see depends entirely on where you are. First, the perspective of an outside observer. Imagine you are floating safely in space, far from a black hole, and you watch your friend fall toward it. Your friend waves goodbye and begins falling. At first, things look normal. Your friend accelerates toward the black hole, falling faster and faster. But as they approach the event horizon, something strange happens. They appear to slow down. Not because they are actually slowing down. From their own perspective, they are still falling freely, still accelerating, but because the light they are emitting back toward you is struggling to climb out of the gravitational field. Time itself, as measured by the light signals reaching you, is slowing down for your friend relative to you. This is gravitational time dilation, one of the key predictions of general relativity. The closer your friend gets to the event horizon, the slower their time appears to pass from your perspective. Their movements become sluggish. Their words, if they are radioing you, become deeper and slower, stretched out, and simultaneously, the light from your friend is being gravitationally redshifted. Their flashlight, which was emitting white light, shifts to yellow, then orange, then red, then deep crimson, then infrared, then microwave, then radio waves. They are fading, getting dimmer and dimmer, getting redder and redder, and from your perspective, your friend never actually reaches the event horizon. They asymptotically approach it, getting closer and closer, but never quite arriving. Their image freezes on the edge, dimmer and dimmer, redder and redder, until they fade below the threshold of detectability and effectively vanish. But they never cross. This is not because the event horizon is an impenetrable barrier. It is because the information about them crossing the event horizon can never reach you. The light that would carry that information is trapped. From your perspective, as an outside observer, your friend is frozen in time on the edge of the event horizon for eternity. But now consider the second perspective, your friends. From their own point of view, the experience is completely different. They feel nothing unusual as they cross the event horizon. There is no wall, no barrier, no flash of light, no sensation of crossing a boundary. For a sufficiently large black hole, a supermassive black hole for instance, the event horizon is actually a very gentle place in terms of local curvature. The region around the event horizon is not particularly different from the flat space far away, at least locally. Your friend would not know they had crossed the event horizon unless they had done a very precise calculation beforehand about their position. This is one of the most counterintuitive aspects of general relativity. The event horizon is a global property of spacetime, not a local one. Locally, at the event horizon, spacetime is perfectly smooth and well-behaved. It is only globally, when you consider the entire spacetime structure, that the event horizon has its remarkable properties. So your friend crosses the event horizon and does not notice. But they are now trapped. Even if they had the most powerful rocket engine in the universe, they could not escape. Why not? Because inside the event horizon, the structure of space-time itself has changed in a way that is almost impossible to convey in everyday language. Inside the event horizon, the radial direction, the direction pointing toward and away from the singularity, takes on the character of a time direction, and the time direction takes on the character of a space direction. The roles of space and time are, in a sense, swapped. What does this mean practically? It means that moving toward the singularity is not like moving toward a place. It is like moving toward a time. It is like moving toward the future. And just as you cannot avoid moving into the future in normal space-time, you cannot avoid moving toward the singularity inside a black hole. The singularity is not a place at the center of the black hole, not really. It is a moment in the future. It is a time, not a place, and reaching it is as inevitable as tomorrow. This is worth sitting with for a moment because it is one of the most profound and mind-bending consequences of general relativity. Inside the event horizon of a Schwarzschild black hole, the singularity is your future, not the place you are heading toward. Your future. It is a moment in time that you will inevitably reach, just as surely as you will reach 5 seconds from now. No amount of acceleration, no clever maneuvering, no technology, nothing can prevent it. Moving away from the singularity inside the event horizon is as impossible as moving backward in time outside it. As your friend falls deeper into the black hole, after crossing the event horizon, the tidal forces begin to grow. Tidal forces are the difference in gravitational pull between different parts of your body. Your feet, being closer to the singularity, are pulled harder than your head, which is farther away. This difference stretches you vertically. Simultaneously, your sides are compressed horizontally, because gravity is pulling them toward the center from slightly different directions. The combined effect is a stretching in one direction and a compression in the perpendicular directions. Stephen Hawking colorfully named this process spaghettification because you are literally stretched into a long, thin strand like spaghetti. For a stellar black hole, say 10 times the mass of the Sun, the tidal forces are already lethal well before you reach the event horizon. A human falling toward such a black hole would be torn apart, stretched into a stream of atoms, before they even crossed the event horizon. But for a supermassive black hole, say 1 billion solar masses, the event horizon is so large and the tidal forces at the event horizon are so relatively mild that a human could cross the event horizon alive and intact. You might survive for several hours inside the event horizon before tidal forces became dangerous. But eventually, inevitably, the tidal forces grow without bound. First, they would tear apart your body, then your cells, then your molecules, then your atoms, then even the subatomic particles themselves. Everything is stretched and compressed to a thinner and thinner strand as the singularity approaches. And then the singularity arrives. According to general relativity, after a finite amount of time, as measured by your friend's own clock, their proper time, they reach AR equals 0. They reach the singularity. And here, according to our theory, the curvature of spacetime becomes infinite. The tidal forces become infinite. The density becomes infinite. And the world line, the trajectory through spacetime, simply ends, stops. There is no more. The singularity is not a transition to somewhere else. It is not a gateway. It is not a portal. In the Schwarzschild solution, it is the absolute end, the termination of space-time itself. Time does not continue past the singularity. Space does not exist at the singularity. The very fabric of reality has reached its boundary, its edge, its end. And our physics has nothing to say about it. Nothing at all. But here is the question that should be burning in your mind right now if you have been following along carefully. Does nature actually produce infinities? Throughout the entire history of physics, every time our theories have predicted infinity, it has turned out that the theory was wrong, or at least incomplete, at that extreme. The infinity was a signal that we needed a better theory, not a description of actual reality. Is the singularity different? Is it the one case where infinity is real? Or is it, like every other infinity before it, a signal that general relativity is incomplete, that it breaks down at extreme conditions and needs to be replaced by something deeper? Most physicists believe the latter. Most physicists believe that the singularity, as predicted by general relativity, does not actually exist. That something else happens at the core of black holes and at the beginning of the universe. But to understand what that something else might be, we need to bring in the other great pillar of modern physics, quantum mechanics. And the collision between quantum mechanics and general relativity at the singularity is one of the deepest and most fascinating stories in all of science. I want to pause here for a moment and acknowledge something. We have been on this journey together for a while now, and we have covered an enormous amount of ground. We started with Newton, moved through Einstein, explored the Schwarzschild solution, watched massive stars collapse, proved that singularities are inevitable with Penrose, and journeyed inside a black hole all the way to the singularity. If you have made it this far, you are genuinely engaged with this material, and I respect that deeply. This is not easy stuff. This is the kind of science that most people encounter only in the most simplified, watered-down form. But you are here, engaging with the real depth of it. So if you have not already, please subscribe to the channel and hit the bell icon for notifications. I make content like this because I believe deeply that people want to understand the universe at a genuine level, not just at a surface level. And your subscription tells me that I am right. And leave a comment. Where are you watching from? What city? What country? Is it daytime or nighttime where you are? Are you on your couch, at your desk, on a bus, lying in bed at 3 in the morning, unable to sleep? I genuinely want to know. This is a community, and I want to understand who is in it. All right, let us talk about quantum mechanics and why it matters so desperately for our understanding of singularities. We have two fundamental theories of physics, two frameworks that together describe virtually everything we observe in the universe. The first is general relativity, which we have been discussing at length. It describes gravity, spacetime, and the behavior of the universe at large scales, stars, galaxies, the cosmos. The second is quantum mechanics, which describes the behavior of matter and energy at the smallest scales, atoms, electrons, photons, quarks. Both theories are spectacular successes. General relativity has been confirmed by every experimental test ever devised for it. Quantum mechanics, in its modern form as quantum field theory, is the most precisely tested theory in all of science. The predicted magnetic moment of the electron, calculated using quantum electrodynamics, agrees with experiment to more than 10 decimal places. That is like predicting the distance from New York to Los Angeles and being accurate to within a fraction of the width of a human hair. But here is the problem. These two theories are fundamentally incompatible. They are built on different assumptions, use different mathematical frameworks, and make contradictory predictions in extreme situations. General relativity treats spacetime as a smooth, continuous fabric that curves and bends. Quantum mechanics treats everything as discrete, quantized, subject to uncertainty and probability. In everyday life, this is not a problem because the regimes where each theory is important do not overlap. Gravity is important for big things, quantum mechanics for small things, and big things are never small things. So the two theories never need to be used simultaneously, except at a singularity. A singularity is where you have an enormous amount of mass compressed into an infinitesimally small space. It is big and small at the same time. It is both a gravitational extreme, requiring general relativity, and a quantum extreme, requiring quantum mechanics. It is literally the point where the two theories collide, and neither one alone can describe what happens. Let me explain this more concretely. Quantum mechanics includes a principle called the Heisenberg uncertainty principle, which states that you cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you know one, the less precisely you can know the other. This is not a limitation of our measuring instruments. It is a fundamental property of nature. Particles do not have simultaneously well-defined positions and momenta. Now, a classical singularity is supposed to be a point, a single location with zero size. That means its position is known with infinite precision, with zero uncertainty. But the uncertainty principle says that if the position uncertainty is zero, the momentum uncertainty must be infinite. Infinite momentum means infinite energy, and infinite energy means the gravitational effects are infinite, which changes the space-time geometry, which changes the singularity, which changes everything. the whole picture becomes self-contradictory. Quantum mechanics simply does not allow a true point of zero size and infinite density. The uncertainty principle forbids it. There is another quantum mechanical concept that is crucial here: quantum fluctuations. At the very smallest scales, the fabric of space-time itself should be subject to quantum fluctuations. Just as the electromagnetic field has quantum fluctuations that produce virtual particles popping in and out of existence, the gravitational field, which is the curvature of space-time, should also fluctuate. At scales much larger than the Planck scale, these fluctuations are negligible. Space-time appears smooth and continuous, and general relativity works perfectly. But at the Planck scale, these fluctuations become violent and dominant. Space-time becomes a roiling, turbulent foam, sometimes called quantum foam or space-time foam. The very concepts of distance and duration lose their meaning. Space-time itself is no longer a smooth manifold, but something fundamentally different. What is the Planck scale? It is defined by three fundamental constants of nature: the gravitational constant g, Planck's constant h bar, and the speed of light c. From these three constants, you can construct a fundamental length, a fundamental time, and a fundamental energy. The Planck length is approximately 1.6 times 10 to the negative 35 meters. That is unimaginably small. An atom is about 10 to the negative 10 meters. A proton is about 10 to the negative 15 meters. The Planck length is 20 orders of magnitude smaller than a proton. It is as small compared to an atom as an atom is compared to the observable universe. The Planck time is approximately 5.4 times 10 to the negative 44 seconds. The time it takes light to travel one Planck length. The Planck energy, or equivalently the Planck mass, is the scale at which quantum gravitational effects become important. Now, a classical singularity has zero size. Zero. That is far, far below the Planck length. At the Planck scale, quantum gravitational effects are important. Below the Planck scale, they are completely dominant. A singularity with its zero size is infinitely below the Planck scale. So any description of a singularity that does not include quantum gravity is almost certainly wrong. General relativity, which is a classical theory that treats space-time as smooth and continuous, cannot be trusted at or near a singularity. Its prediction of infinite density and zero size is not a description of reality. It is a description of the failure of the theory. The infinity is a signal that we have pushed general relativity beyond its domain of validity, and we need a theory of quantum gravity to understand what actually happens. This brings us to one of the most famous and important results in theoretical physics of the past 50 years: Hawking radiation and the black hole information paradox. In 1974, Stephen Hawking made a discovery that stunned the physics world. He showed that black holes are not, in fact, perfectly black. They radiate. This might sound contradictory. We said earlier that nothing can escape from inside the event horizon, and that remains true. Hawking radiation does not come from inside the event horizon. It comes from the event horizon itself, or rather, from the quantum vacuum fluctuations just outside the event horizon. Here is the basic idea, simplified. In quantum field theory, the vacuum of space is not truly empty. It is filled with virtual particle-antiparticle pairs that constantly pop into existence and then annihilate each other in an incredibly short time. This is a consequence of the uncertainty principle applied to energy and time. Near the event horizon of a black hole, something unusual can happen. A virtual particle pair pops into existence just outside the event horizon. Normally, the two particles would annihilate. But if one of the particles falls into the black hole before annihilation can occur, the other particle can escape to infinity. This escaped particle carries positive energy. The particle that fell in can be thought of as carrying negative energy, which reduces the mass of the black hole. The net effect is that the black hole emits radiation, real particles streaming outward, while simultaneously losing mass. This is Hawking radiation. It is an extraordinary result because it combines quantum mechanics, the virtual particle pairs, general relativity, the event horizon, and thermodynamics. The radiation has a thermal spectrum like a warm body. It means that black holes have a temperature. For a stellar black hole, this temperature is incredibly low, about 60 billionths of a Kelvin above absolute zero, far colder than the cosmic microwave background radiation that fills the universe. So stellar black holes absorb more radiation from their environment than they emit, and they actually grow over time. But in principle, if you put a black hole in perfectly empty space and waited long enough, it would slowly radiate away its mass and eventually evaporate completely. How long would this take? For a stellar black hole, say 10 times the mass of the Sun, the evaporation time is approximately 10 to the 67th years. That is a 1 followed by 67 zeros. To put this in perspective, the current age of the universe is about 1.4 times 10 to the 10th years, about 14 billion years. The evaporation time for a stellar black hole is roughly 10 to the 57th times the current age of the universe, an incomprehensibly vast span of time. For a supermassive black hole, the evaporation time is even more extreme, on the order of 10 to the 100th years. But the point is that it is finite. Given enough time, every black hole will evaporate. Every single one. And this creates a profound problem, a problem so deep that it has been called the biggest crisis in theoretical physics. It is called the black hole information paradox. Here is the paradox. One of the fundamental principles of quantum mechanics is unitarity. Unitarity means that the total amount of information in a closed system is conserved. Information can be scrambled, mixed up, hidden in incredibly complex ways, but it is never destroyed. In principle, if you know the complete quantum state of a system at one time, you can calculate its state at any other time, both forward and backward. This is a bedrock principle of quantum mechanics. It has been tested and confirmed countless times. Without it, the mathematical structure of quantum theory falls apart. Now, imagine you throw a book into a black hole. The book crosses the event horizon and, according to general relativity, eventually hits the singularity. The information in the book, every word, every letter, every quantum state of every particle in the book, is now at the singularity, a point where physics breaks down. Now, wait. Wait for an unimaginably long time. Wait for 10 to the 67th years or however long it takes. The black hole evaporates via Hawking radiation. Every last bit of its mass is radiated away. The black hole is gone. Completely. Nothing remains. So, where is the information from the book? Hawking's original calculation showed that Hawking radiation is perfectly thermal. It has a smooth, featureless spectrum that depends only on the temperature of the black hole, which depends only on its mass. the radiation carries no information about what fell into the black hole. A black hole formed from the collapse of a star made of hydrogen would emit exactly the same Hawking radiation as a black hole of the same mass formed from the collapse of a star made of iron, or a black hole formed from the collapse of 1 billion encyclopedias. The Hawking radiation contains no information about the internal state, so when the black hole has completely evaporated, the information has apparently been destroyed. The book is gone. Its information is gone. Unitarity has been violated. Quantum mechanics has been broken. This is the information paradox. Either quantum mechanics is wrong, unitarity is violated, and information can be destroyed, or Hawking's calculation is wrong. Hawking radiation does carry information somehow, or there is something else going on that we do not understand. Hawking himself initially argued that information is truly destroyed in black holes, which would mean that quantum mechanics needs to be modified. Most other physicists, including notably Leonard Susskind and Gerard 't Hooft, refused to accept this. They argued that unitarity must be preserved, and that there must be a mechanism by which information escapes. This debate raged for decades. In 2004, Hawking famously conceded, publicly announcing that he now believed information is preserved, though he admitted he was not sure how. He paid off a bet he had made with John Preskill years earlier, giving him a baseball encyclopedia, information from which could be recovered at will. But Hawking's concession did not solve the problem. It just shifted the question from, is information destroyed, to how does information escape? The information paradox is intimately connected to the singularity. If the singularity is real, if it is truly a point where space-time and physical law cease to exist, then it is hard to see how information could be preserved. The singularity would be the place where information goes to die. But if the singularity is resolved by quantum gravity, if something else happens instead of infinite density, then perhaps information is preserved after all, stored in whatever replaces the singularity, and gradually released as the black hole evaporates. Solving the information paradox may require solving the singularity. In recent years, there has been significant progress on the information paradox. In 2019 and 2020, theoretical physicists including Netta Engelhardt, Ahmed Almheri, Jeffrey Pennington, and Henry Maxfield developed what is called the island formula, which showed that if you properly account for quantum gravitational effects, the entropy of Hawking radiation follows the expected Page curve, named after Don Page, who proposed it in 1993. The Page curve describes how the entropy of the radiation initially increases as the black hole evaporates, then decreases, eventually returning to its initial value. This is exactly what unitarity predicts, and what Hawking's original calculation could not reproduce. The island formula reproduces the Page curve by identifying island regions inside the black hole whose information is actually owned by or accessible to the radiation outside. This was a major breakthrough, widely regarded as the most important advance in the information paradox in decades. But it does not resolve everything. The island formula works within a semi-classical approximation and relies on the ADS/CFT correspondence, a theoretical framework that relates gravitational theories in certain curved spacetimes to non-gravitational quantum theories on their boundaries. Whether these results apply to the real universe, which is not an anti-de Sitter spacetime, remains an open question. And the formula does not tell us in detail what happens at or near the singularity. It suggests that the interior geometry of a black hole is more complex than the simple picture of a smooth space-time leading to a singularity. But the details remain shrouded in mystery. There is another paradox closely related that emerged in 2012 and further illuminated the tension between quantum mechanics and singularities. It is called the AMPS Firewall paradox, named after its proposers, Ahmed Almheri, Donald Maroff, Joseph Polchinski, and James Sully. The firewall paradox sharpens the information paradox by showing that three seemingly reasonable assumptions cannot all be true simultaneously. First, that Hawking radiation carries information, unitarity is preserved. Second, that the event horizon is smooth, with no drama for an infalling observer, the equivalence principle, a cornerstone of general relativity. Third, that physics outside the event horizon is described by standard quantum field theory. AMPS showed that if information is indeed carried away by Hawking radiation, then the radiation must be highly entangled in a specific way. But this entanglement is incompatible with the smoothness of the event horizon. Instead, what should happen is that the entanglement structure at the event horizon breaks down, creating a violent burst of high-energy particles. This violent region at the event horizon is the firewall. It means that instead of smoothly crossing the event horizon and falling toward the singularity, you would be incinerated the moment you touched the event horizon. This was deeply disturbing because the smoothness of the event horizon is a core prediction of general relativity. The equivalence principle, the very foundation of GR, says that a freely falling observer should not notice anything special at the event horizon. The firewall paradox seemed to force a choice. Either give up unitarity, information is lost, or give up the equivalence principle, firewalls exist, or give up standard quantum field theory outside the event horizon. None of these options is palatable. Leonard Susskind and Juan Maldacena proposed a provocative response in 2013 known as the ER equals EPR conjecture. They suggested that quantum entanglement between particles, EPR, named after the Einstein-Podolsky-Rosen paradox, is physically connected to Einstein-Rosen bridges, which are wormholes in space-time, ER, for Einstein and Rosen, who first described them. In other words, every pair of entangled particles is connected by a tiny non-traversable wormhole. This would mean that the interior of a black hole is not disconnected from the exterior. It is connected through a complex network of wormholes/entanglement. In this picture, the firewall is avoided because the entanglement structure is maintained through the wormhole connections. Information can get from inside the black hole to the outside through this entanglement/wormhole network, not by traveling faster than light, but because the inside and outside are, in a deep sense, not fully separate. ER equals EPR is a beautiful and speculative idea. If true, it would profoundly change our understanding of the relationship between space-time and quantum entanglement. It would suggest that space-time itself is woven from entanglement, that the connectivity of space is a consequence of the quantum correlations between particles. This is related to the broader program of understanding space-time as emergent as arising from a more fundamental quantum substrate, which we will discuss more shortly. But ER equals EPR remains a conjecture. It has not been proven, and its full implications for the singularity are still being worked out. All of these paradoxes and conundrums have one thing in common. They all converge on the singularity. The information paradox is about what happens to information that reaches the singularity. The firewall paradox is about the entanglement structure that is influenced by the singularity. The cosmic censorship conjecture is about whether the singularity's unpredictability is contained. Every deep problem in black hole physics ultimately traces back to the singularity. Resolve the singularity, and many of these problems might dissolve. Fail to resolve it, and they remain as stubborn and perplexing as ever. Now let us expand our view and talk about the other singularity in the universe's history. Not the one at the center of black holes, but the one at the very beginning of everything. The Big Bang singularity. The evidence for the Big Bang is overwhelming. Let me walk you through the key pieces. In 1929, the American astronomer Edwin Hubble made one of the most important observations in the history of science. He discovered that nearly all galaxies are moving away from us, and the farther away a galaxy is, the faster it is receding. This is Hubble's law, and it implies something extraordinary. If all galaxies are moving apart now, then in the past, they were closer together. Run the expansion backward in time, and all the galaxies converge, getting closer and closer, until at some point, in the distant past, all the matter in the observable universe was concentrated in an incredibly small, incredibly dense, incredibly hot state. This is the Big Bang. The most powerful piece of evidence for the Big Bang is the cosmic microwave background radiation, or CMB. In 1965, Arno Penzias and Robert Wilson, two radio astronomers at Bell Laboratories in New Jersey, accidentally discovered a faint, uniform glow of microwave radiation coming from every direction in the sky. They could not figure out what was causing it. They checked their equipment, cleaned pigeon droppings off their antenna, and redid their measurements. But the signal persisted. It turned out that what they had discovered was the afterglow of the Big Bang itself. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form, and light could travel freely for the first time. That light has been traveling through space ever since, stretched by the expansion of the universe from its original high-energy form into the microwaves we detect today. The CMB has a nearly perfect thermal blackbody spectrum with a temperature of about 2.725 Kelvin, and it is the most perfect thermal spectrum ever measured. It is also remarkably uniform, with temperature variations of only about 1 part in 100,000 across the sky. These tiny variations correspond to slight density fluctuations in the early universe that eventually grew into the galaxies and galaxy clusters we see today. The CMB is our snapshot of the universe at age 380,000 years, and it matches the predictions of the Big Bang theory with extraordinary precision. Another piece of evidence is Big Bang nucleosynthesis. In the first few minutes after the Big Bang, when the universe was a roiling soup of protons, neutrons, electrons, and photons at temperatures of billions of degrees, nuclear fusion occurred. Protons and neutrons fused to form the lightest elements, hydrogen, helium, and tiny amounts of lithium and beryllium. The Big Bang theory predicts very specific abundances of these light elements, roughly 75% hydrogen and 25% helium by mass, with trace amounts of deuterium, helium-3, and lithium-7. When we look out at the oldest, most pristine regions of the universe, the observed abundances of these elements match the predictions beautifully. This is a powerful confirmation that the early universe was, indeed, incredibly hot and dense, exactly as the Big Bang theory describes. Now, here is where the singularity comes in. If we take the observed expansion of the universe and trace it backward using general relativity, we find that the universe gets smaller, denser, and hotter as we go further into the past. And if we keep going all the way back, the math says that at a finite time in the past, approximately 13.8 billion years ago, the scale factor of the universe reaches 0. The entire observable universe is compressed into a single point. The density, temperature, and curvature of spacetime all become infinite. This is the Big Bang singularity. According to general relativity, the universe began from a state of infinite density and infinite temperature. All of space and time emerged from this singularity. There is no before the Big Bang in this picture, not because we are ignorant of what came before, but because time itself began at the singularity. Asking what came before the Big Bang is like asking what is north of the North Pole. The question does not have a meaningful answer because the concept of north ends at the North Pole, just as the concept of before ends at the Big Bang. But the Big Bang model, as successful as it is in explaining the observed features of the universe, has some problems that suggest the simple picture of a singularity at t=0 may not be the whole story. The first is the horizon problem. The cosmic microwave background is extraordinarily uniform, with the same temperature in every direction to 1 part in 100,000. But here is the puzzle. Different parts of the sky, particularly regions that are on opposite sides of the sky, have never been in causal contact. Light has not had enough time since the Big Bang to travel from one side to the other. So how did these regions reach the same temperature? In everyday life, things reach the same temperature by being in contact, by exchanging heat. But in the standard Big Bang model, these regions were never in contact. They should have wildly different temperatures, but they don't. They are almost exactly the same. This demands an explanation. The second is the flatness problem. Observations show that the geometry of the universe is extremely close to flat, meaning it has zero spatial curvature on large scales. In general relativity, the curvature of the universe evolves over time, and any initial deviation from flatness gets amplified as the universe expands. For the universe to be as flat as we observe it today, 13.8 billion years after the Big Bang, the curvature at the Big Bang would have had to be fine-tuned to an almost inconceivable degree of precision. We are talking about 1 part in 10 to the 60 or so. This extreme fine-tuning seems deeply unnatural and cries out for an explanation. In 1981, the American physicist Alan Guth proposed a solution to both problems: cosmic inflation. Inflation is the idea that in the very, very early universe, in the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid exponential expansion. In a time span of roughly 10 to the negative 36 to 10 to the negative 32 seconds, the universe expanded by a factor of at least 10 to the 26, and possibly much, much more. Regions that are now on opposite sides of the observable universe were, before inflation, in causal contact. They were close enough together to reach the same temperature. Then inflation stretched them far apart, explaining why the CMB is so uniform. Inflation also explains flatness. The enormous expansion stretched any initial curvature to effective flatness, just as blowing up a balloon makes a small patch of its surface look flat. Inflation has become a cornerstone of modern cosmology. It makes additional predictions, including the specific pattern of temperature fluctuations in the CMB, and these predictions match observations remarkably well. But here is the crucial question for our story. Does inflation eliminate the Big Bang singularity? The answer is, not necessarily. Inflation pushes the singularity further into the past and makes the approach to it smoother, but it does not remove it. In 2003, Arvind Borde, Alan Guth, and Alexander Vilenkin proved a theorem, the BGV theorem, which states that any universe that has been, on average, expanding throughout its history must have a beginning. Specifically, there must be a past boundary to spacetime. This does not necessarily mean the boundary is a singularity in the GR sense, but it means the universe cannot be past eternal within the framework of inflation plus general relativity. Something happened at the beginning, and that something is related to the singularity question. Several alternatives to the Big Bang singularity have been proposed, each representing a different way of thinking about how the universe began, or whether began is even the right word. One is bouncing cosmology. In this picture, the universe did not begin from a singularity. Instead, it contracted from a previously large state, reaching a minimum but non-zero size, and then bounced back and began expanding. The Big Bang, in this view, was really a big bounce. There was a universe before the bounce, and there will be a universe after. The singularity is avoided because the universe never reaches zero size. Various mechanisms have been proposed for what causes the bounce, including quantum gravitational effects, violation of certain energy conditions, or extra dimensions. Another is the cyclic model proposed by Paul Steinhardt and Neil Turok. In their picture, the universe goes through an infinite sequence of cycles: expansion, contraction, bounce, expansion, contraction, bounce, on and on forever. Each cycle includes a period that looks like a Big Bang, but there is no ultimate beginning and no singularity. The cycles are driven by the interactions of membranes, brains, in a higher dimensional space, inspired by string theory. A third, and perhaps the most famous, is the Hartley-Hawking no-boundary proposal. In 1983, James Hartle and Stephen Hawking proposed that the universe has no boundary in the past. It does not begin at a singularity. Instead, near the beginning, the nature of time changes. Using a mathematical technique called Wick rotation, you can transform the time coordinate into a spatial coordinate. In this picture, as you go further and further back in time, time gradually becomes space-like. The singularity is smoothed out. The universe has no edge, no beginning, no boundary, just as the surface of a sphere has no edge. The geometry is smooth and well-defined everywhere. Hawking described it this way: asking what came before the Big Bang in the no-boundary proposal is like asking what is south of the South Pole. The question simply does not apply. And perhaps the most physically motivated alternative comes from loop quantum cosmology, which we will discuss more in a moment. where quantum gravitational effects prevent the universe from ever reaching zero size. Instead of a Big Bang singularity, there is a big bounce at the Planck density, where quantum gravity effects become dominant and reverse the collapse. Each of these proposals replaces the Big Bang singularity with something more palatable. Each avoids the problem of infinite density, infinite temperature, and the breakdown of physics. But none of them has been definitively confirmed by observations. They remain theoretical proposals, and distinguishing between them observationally is an enormous challenge. The precise nature of the very early universe, the first tiny fractions of a second, remains one of the great frontiers of cosmology. Now, let me ask you something. We have been talking about singularities for a while now, and I have repeatedly said that most physicists believe singularities are not real, that they are artifacts of the breakdown of general relativity. So what do physicists think actually happens at the core of a black hole or at the beginning of the universe? What replaces the singularity? To answer this, we need to talk about the quest for quantum gravity, the holy grail of theoretical physics, the theory that would unify general relativity and quantum mechanics, and hopefully resolve the mystery of singularities once and for all. The need for a theory of quantum gravity has been recognized for nearly a century. We know that GR and QM are both correct in their respective domains, but they cannot both be correct everywhere. A unified theory must exist that reduces to GR in the large-scale, low-curvature limit and to QM in the small-scale, low-gravity limit, but that gives new correct answers in extreme conditions where both gravity and quantum effects are important. The singularity is the most extreme of these extreme conditions. It is the ultimate test case for any theory of quantum gravity. The problem is that constructing a theory of quantum gravity has proven to be extraordinarily difficult. It is perhaps the hardest problem in all of theoretical physics. The standard techniques that were used to quantize the electromagnetic force, the strong nuclear force, and the weak nuclear force fail when applied to gravity. When you try to apply the usual perturbative quantum field theory methods to general relativity, you get infinities that cannot be removed by the standard procedure of renormalization. The theory is said to be non-renormalizable, which means that its predictions at high energies are not well defined. This is not just a technical nuisance, it is a fundamental obstacle. Moreover, the scale at which quantum gravitational effects become important, the Planck scale, is almost inconceivably far from anything we can directly probe experimentally. The Planck energy is about 10 to the 19 giga-electron volts. The most powerful particle accelerator ever built, the Large Hadron Collider at CERN, reaches energies of about 10 to the 4th giga-electron volts, 15 orders of magnitude below the Planck energy. It would take a particle accelerator roughly the size of the Milky Way galaxy to directly probe the Planck scale. We may never be able to directly test quantum gravity with particle accelerators. This means that any theory of quantum gravity must be guided primarily by theoretical consistency, mathematical elegance, and indirect observational hints, rather than by direct experimental evidence. This makes the problem even harder, because without experimental guidance, it is very easy to go astray. Despite these immense challenges, there are several major approaches to quantum gravity, each with its own ideas about what happens at singularities. Let me describe the most important ones. The first and most famous is string theory. String theory proposes that the fundamental objects in nature are not zero-dimensional point particles, but one-dimensional objects called strings. These strings are extraordinarily tiny, roughly the Planck length in size. They can vibrate in different modes like the strings of a guitar, and each vibrational mode corresponds to a different particle. One mode gives you an electron, another gives you a quark, another gives you a photon, and crucially, one mode gives you the graviton, the hypothetical quantum of the gravitational field. In this way, string theory naturally incorporates gravity at the quantum level. It is a theory of quantum gravity by construction. String theory has several implications for singularities. First, because strings have a finite size, the Planck length, they cannot be compressed to a true point. The concept of a point singularity, a zero-dimensional object of infinite density, is not compatible with string theory. What looks like a singularity from the perspective of general relativity might, at the string scale, reveal itself to be a smooth, finite structure. Second, string theory contains mechanisms for resolving singularities that do not exist in general relativity. Certain types of singularities in string theory, particularly time-like singularities in certain geometries, have been successfully resolved using string theoretic techniques. The singularity is replaced by a smooth, well-defined geometry when stringy effects are taken into account. One particularly intriguing proposal within string theory is the fuzzball conjecture, developed primarily by Samir Mathur at Ohio State University. According to the fuzzball picture, what we call a black hole is not a region of space-time with an event horizon and a singularity at the center. Instead, it is a compact, horizonless object made of strings and branes, higher dimensional objects that also appear in string theory. The fuzzball has the same mass, charge, and angular momentum as the corresponding black hole, so from a distance it looks identical to a black hole. But up close, it is completely different. There is no event horizon. There is no singularity. Instead, there is a complex quantum gravitational structure that extends all the way to where the event horizon would have been. The information of everything that has ever fallen into the black hole is stored on the surface of the fuzzball, like data encoded on a hard drive. This naturally resolves the information paradox, because information is never lost and never reaches a singularity. It is always stored on the fuzzball's surface. The fuzzball proposal is a radical reimagining of what a black hole is. If correct, it means that singularities simply do not exist. Every black hole is a fuzzball with no singularity and no event horizon, just a complicated quantum gravitational object. But the proposal is controversial. Not all string theorists agree with it. And computing the detailed properties of fuzzballs for astrophysically realistic black holes, rotating and massive, is extraordinarily difficult. The idea remains an active area of research. String theory as a whole has been both spectacularly successful and frustratingly incomplete. It provides a mathematically consistent framework for quantum gravity, which is no small achievement. It has led to deep insights into the nature of space-time, the holographic principle, and the connection between gravity and quantum information. But it has also been criticized for its lack of unique predictions. The theory appears to admit an enormous number of possible solutions, a vast landscape of possibilities estimated at 10 to the 500th or more. Which solution describes our actual universe? We do not know. String theory also requires extra dimensions of space, either 6 or 7 depending on the formulation, beyond the 3 we experience. These extra dimensions must be compactified, rolled up so small that we do not see them. But the way they are compactified determines the physics we observe, and there are vast numbers of ways to do it. This makes it very hard to extract specific, testable predictions from string theory. Despite decades of work by thousands of brilliant physicists, string theory has not yet produced a prediction that has been confirmed by experiment. This does not mean it is wrong, but it does mean we cannot yet be sure it is right. The second major approach to quantum gravity is loop quantum gravity, often abbreviated LQG. Loop quantum gravity takes a fundamentally different approach from string theory. Instead of starting with particles and extending them to strings, LQG starts with general relativity and quantizes it directly. The result is a theory in which space-time itself has a discrete quantized structure at the Planck scale. In LQG, space is not a smooth continuum. It is made of discrete chunks, atoms of space, connected in a network called a spin network. The areas of surfaces and the volumes of regions of space come in discrete quanta, analogous to how the energy levels of atoms are discrete. There is a minimum area, roughly the Planck area, about 10 to the negative 70 square meters, and a minimum volume, roughly the Planck volume. Space is granular, like a mosaic, with tiles of the Planck size. The implications for singularities are profound. If space has a minimum size, then the concept of a point singularity is meaningless. You cannot compress something to a size smaller than the Planck length because smaller sizes do not exist. The singularity is replaced by a region of Planck scale physics, incredibly dense but finite. Specific calculations in loop quantum gravity have shown what happens when you apply the theory to the interior of a black hole and to the early universe. For black holes, the singularity is resolved. Instead of an infinitely dense point, the collapse reaches Planck density, roughly 10 to the 93 grams per cubic centimeter. At this density, quantum gravitational effects become dominant. A new kind of repulsive force emerges, a quantum pressure arising from the discreteness of space, which halts the collapse. The singularity is replaced by a compact, incredibly dense object, sometimes called a Planck star. This Planck star has finite density, finite curvature, finite everything. The infinities are gone. And here is the truly fascinating part. The Planck star may not last forever. Over immense periods of time, it may bounce, expanding outward, transitioning from a black hole to a white hole. A white hole is the time reverse of a black hole, an object from which things can only come out, never go in. In this picture, matter falls into a black hole, reaches Planck density, pauses for an astronomically long time from the outside perspective, but possibly only a short time in the local frame, and then bounces back out as a white hole. The singularity is not an end, it is a transition. For the Big Bang, loop quantum cosmology makes an even more dramatic prediction. Applying LQG to the early universe, the Big Bang singularity is replaced by a big bounce. The universe did not begin from a singularity. It contracted from a previously large state, reached Planck density, and then bounced, transitioning from contraction to expansion. The Big Bang was not the beginning of time. It was a transition from a prior contracting phase to our current expanding phase. The universe may have existed before the Big Bang in some form, and the singularity, with its infinite density and the breakdown of physics, never happened. Loop quantum gravity, like string theory, has its strengths and its weaknesses. Its strength is that it provides a clear, well-defined resolution of singularities based on the fundamental discreteness of space. Its weakness is that it is not yet a complete theory. There are unresolved mathematical issues, particularly in extending the theory from simplified models to the full four-dimensional case. And like string theory, it has not yet produced a prediction that has been uniquely confirmed by experiment. The two approaches are complementary in some ways and competitive in others. Most physicists working in either field would acknowledge that neither approach is complete, and that the final theory of quantum gravity might look quite different from either one. There are several other approaches to quantum gravity that I want to mention briefly, because each offers its own perspective on singularities. Causal set theory proposes that space-time is fundamentally a discrete set of points, called events, connected by causal relationships. Instead of a smooth continuum, space-time is a network, a causal set. The density of events corresponds to the volume of space-time. In this framework, the concept of a smooth singularity does not arise because there is no smooth space-time to be singular. The singularity might be replaced by a region where the causal structure becomes degenerate in some specific way, but infinite densities and curvatures are avoided because the continuum approximation breaks down before they are reached. Asymptotic safety is an approach based on the idea that the gravitational interaction, while non-renormalizable perturbatively, might be non-perturbatively well behaved. Specifically, it is proposed that there exists a fixed point in the space of gravitational couplings at high energies, at which the theory becomes finite and predictive. If this is the case, then gravitational physics at the Planck scale is well defined, and singularities might be smoothed out by the high-energy behavior of the gravitational coupling. Non-commutative geometry proposes that the coordinates of space-time do not commute at very small scales. In ordinary geometry, the coordinates x, y, z are just numbers, and numbers commute. X times y equals cos r times x. But in non-commutative geometry, the coordinates are operators, like the position and momentum operators in quantum mechanics, and they do not commute. This introduces a natural minimum length scale, because you cannot specify the coordinates of a point with precision better than the non-commutativity scale. Point singularities are thus impossible, and the singularity is expected to be smeared out into a finite region. Emergent gravity, associated particularly with the work of Eric Verlinde, proposes that gravity is not a fundamental force, but an emergent phenomenon, arising from the collective behavior of more fundamental degrees of freedom, possibly related to quantum information and entropy. In this framework, space-time itself is emergent, and singularities, which are features of the classical space-time description, might simply not exist in the more fundamental description. They would be artifacts of the emergent description, like the singularity at the center of a whirlpool, which is an artifact of the fluid dynamics description and does not correspond to anything fundamental. The holographic principle and the ADS/CFT correspondence, developed primarily by Juan Maldacena in 1997, provide yet another perspective. The holographic principle states that all the information about a region of space can be encoded on its boundary with a density of no more than 1 bit per Planck area. This means that the physics inside a three-dimensional region of space is entirely equivalent to the physics of a two-dimensional theory on the boundary. The ADS/CFT correspondence makes this precise for a particular type of spacetime, anti-de Sitter space, showing that gravity in the interior is exactly equivalent to a quantum field theory without gravity on the boundary. In this framework, the singularity at the center of a black hole in the interior corresponds to some perfectly well-defined state in the boundary theory. The boundary theory does not have singularities. It is a standard quantum field theory. So the singularity is, in a sense, an artifact of the gravitational description. In the more fundamental boundary description, everything is smooth and well-defined. This is perhaps the most radical perspective on singularities. They are not features of reality at all, but features of a particular way of describing reality. And in the more fundamental description, they do not exist. What do most physicists actually think about singularities? The honest answer is that there is no consensus because we do not have a complete theory of quantum gravity. But if I had to summarize the majority view, it would be something like this. Singularities, as predicted by general relativity, are real mathematical features of the theory. The Penrose-Hawking theorems prove this rigorously. But most physicists believe that general relativity is not the final theory. It is an effective theory, an incredibly good approximation that works in a vast range of conditions, but breaks down at extreme densities and curvatures. The singularities predicted by GR are signals of its breakdown, not descriptions of reality. In the correct, more fundamental theory of quantum gravity, whatever that theory turns out to be, the singularities will be resolved. Infinite densities will be replaced by finite Planck scale densities. The breakdown of space-time will be replaced by some new quantum gravitational physics that we do not yet fully understand. Most physicists expect that nature does not produce genuine infinities. Every infinity we have ever encountered in physics has been resolved by a deeper theory, and the singularity will be no different. But I want to be honest about the uncertainty here. We do not know this for certain. It is possible, in principle, that singularities are real, that nature does produce genuine infinities, that our intuition about the impossibility of infinity is wrong. It seems unlikely based on the historical pattern, but we cannot rule it out. The question is open, and it will remain open until we have a confirmed theory of quantum gravity. Let me now take us deeper into the classification and structure of singularities, because not all singularities are the same, and the differences between them are fascinating and important. The simplest singularity, the one we have been mostly discussing, is the Schwarzschild singularity. This is the singularity at the center of a non-rotating, uncharged black hole. In the Schwarzschild solution, the singularity is a point, zero-dimensional, with infinite density and curvature. But here is something that surprises many people. The Schwarzschild singularity is not a point in space that sits at the center of the black hole, waiting for things to fall into it. It is a moment in time. Inside the event horizon, as we discussed earlier, the roles of space and time are essentially exchanged. The singularity at r equals 0 is actually a space-like surface, a surface that lies in the future of every infalling observer. You do not travel to the singularity. You arrive at the singularity. It is your future, and it is unavoidable. This is why there is no way to avoid the singularity inside a Schwarzschild black hole. Avoiding it would be like avoiding next Tuesday. The singularity is not a place. It is a time, and time marches forward. But the Schwarzschild black hole is an idealization. Real black holes in the universe rotate. They are formed from rotating stars, and angular momentum is conserved during the collapse. So real black holes have angular momentum, and the geometry of a rotating black hole is described not by the Schwarzschild solution, but by the Kerr solution, found by the New Zealand mathematician Roy Kerr in 1963. The Kerr solution was one of the most important discoveries in the history of general relativity, because all astrophysical black holes rotate. The Kerr solution is vastly more complex than the Schwarzschild solution, and its singularity is different in a fundamental way. The singularity at the center of a rotating black hole is not a point. It is a ring. A one-dimensional ring of zero thickness, but finite circumference, lying in the equatorial plane of the black hole. This is called the ring singularity. The curvature of space-time is infinite on the ring itself, but is finite everywhere else, even at the center of the ring. If you could somehow approach the ring from above or below, perpendicular to the equatorial plane, and pass through the center of the ring, you would experience finite curvature everywhere. You would not be destroyed by infinite tidal forces. You would pass through the ring, and where would you end up? This is where the Kerr solution gets truly mind-bending. According to the mathematics of the Kerr solution, passing through the ring singularity takes you into a different region of space-time. Not a different place in our universe, a different space-time entirely. Some interpretations describe this as a different universe, or a different part of a larger multiverse, or a white hole in another region. The Kerr geometry, when fully extended, describes an infinite sequence of connected universes, linked through ring singularities. In an elaborate structure sometimes called a Penrose diagram or a Carter-Penrose diagram,